Hello and welcome back to the lab. A quick thank you to all of the people who have joined us recently, and definitely a thank you to all the Patreons who helped make this channel possible. You guys are an immense help, and I greatly appreciate it, so thanks again. Today on the bench, the last of the big three for calibrating a scope, TG501. So we took a look at the SG503, the leveled sine wave generator, the PG506, the calibration generator. This one is the time mark generator. And after this video is finished, I'm going to do a video. I've had a lot of requests on what makes these three units special, in quotes. So I'm going to do a deeper dive into these three units and how they're used to calibrate a scope as opposed to just doing the scope calibration. See if I can give some more detail onto what I'm actually doing. This is a very, very early unit. Given the problems I had with the PG506, I'm going to check it for capacitors, things like that, see if it needs to be replaced. If there's anything in there, we'll replace it, and then I'm going to do an alignment on it. I am not going to go through the factory alignment procedure on this one because I believe from the last time I looked at it, which has been a while, you have to do scope frequency analysis, which is waiting for the trace sync on the scope and things like that. In the lab, we have a 255 megahertz frequency counter or universal counter. I'll just do the direct measurement, and then I'll probably end up moving over to the DSA, and we'll do the waveform shaping and things like that on the sampling scope. So calibration on this with modern gears is going to be a lot easier than we had to do it when these initially came out. So serial number on this one is actually 167. So this is a very, very early unit. It's B010167. So super early unit on this. So it'll be interesting to take it apart. Also with the higher frequency outputs, it's pretty interesting to take a look at as well. So let me get the covers off and we'll get into it. I'll prop this up here on the bench to get a better angle for the camera. So we can see the high frequency. This is the high frequency board. Definitely don't want to bend this coil right here. That would be a very fiddly adjustment to get back into rights. I'm going to have to take this board out to get at the board on the bottom, because the board on the bottom is the one I want to check for capacitors and things like that. So we'll unplug the cables. I'll take tech pictures and I'll post those to Patreon like I normally do. So here's the high-speed side of the board. The other side of the board, there's not much there on the back. So to start with, let me get this top board out. I'm going to also see if we can get under this cover, take a look at what's under there. I have a feeling the circuitry will be pretty cool under there. Some high-speed stuff. So let me get in, and I will bring you guys back once I get everything disconnected. Well, in this one, there is not much to do. I can't see any electrolytics in here. Everything looks good. At least in this one, there's a whole bunch of these really crappy sockets, but I'm not having any problems with this one, so I'm going to leave them be. If I do end up having any problems with the sockets, then I'll swap the sockets out at that point. But at this particular point in time, this unit's working okay. These switches over here need to be cleaned while I have the board out. That'll make cleaning those a lot easier. The cables did not come out of the RF deck. That's why I have it just folded over like that. It was 4 screws on the posts and then the 4 screws on the switches. The switches actually look really good in this one. I'm going to oil the shafts just to keep them lubricated with some machine oil. I'm going to clean the switches with alcohol. These are working, so I don't need to do any contact cleaner or anything like that. I'm just going to flush them with alcohol and call it a day. To service those, I'll flush the variable switch as well. We'll service the potentiometer, but other than general control maintenance, not much goes wrong in one of these, which is pretty cool. I expected at least a couple electrolytics in there, but nope. So I'll get that done, and then I will bring everyone back. Okay, well, don't pull the cables out of the enclosure because they're actually soldered in. So the yellow, orange, and green mini coax don't come out. Looks like what's in here is a comb filter, tunable. Every stage is tunable. We have one transistor hiding down here. Nice coil up here. Everything looks like it's tunable. Probably have to adjust all of these during the calibration, so I will see what frequencies these are running at. But that's what's under the shield on the top board. I couldn't open this thing up and not look under the shield, see what was going on, so there we go. Okay, I've given some time for the alcohol to flash off. So let's see. Got the Rigol set up with a 50 ohm terminator to check the output. Let's give it some power. No smoke. And we have time marks. 0.5 milliseconds, 500 microsecond time marks. Actually, that agrees. Very cool. Check a period, see how accurate it is. Next thing will be, because we were in here, we'll be tuning up the alignment. Let's see. What's our GPS DO say? Well, the frequency counter backed up with the reference. Period channel 1. 499.999325. Pretty close. So we'll give it a bit more time. I'll get a cal document out, and then we'll run through a cal document. But I think this guy's going to be ready for the long run. Okay, I've had the lab warming up for a while. I've got the DSA 602 on because I need a sampling scope for the 1 gigahertz sine wave. We've got the frequency counter fired up, which is backed up by the GPS DO as an external reference. There's plenty of satellites in the sky, given the GPS DO's monitoring software. Everything's been warming up for a while, so we are ready to get started with the calibration and alignment. The calibration document on this one is really short from what I'm used to dealing with. It is 3 pages. So super short. This won't take long. It's check some voltages, then check some timing, and then we're done. So this document did use a frequency counter for this. The zero beating that I was remembering was from doing an alignment on the 184. If everybody's interested in that, let me know. I am also looking for a 184 that is broken. So I'd love to find a 184 that mostly works, but the oscillator's dead in it, because I want to see about getting a 184 possibly matched up with a GPS DO. Don't know, something I'm kicking around, rolling around in my head, but I need to find the right unit. So a decent shape 184 with a dead reference crystal would be perfect, but I have yet to find one. So if anybody knows where 184 is that needs some help, let me know, and I will see what we can make happen. So for the preliminary to get set up, let's check the display real quick. You push and hold. We have all 16 digits of the display, so that's good. And then this wants 1 microsecond markers, and we need to check voltages now. But it's telling, the service manual is telling me that R606, which is the 15 volt adjustment, doesn't exist in my unit because it doesn't exist below 31770, and this unit doesn't have option 1, so we have no adjustment. So it's just sanity checking the power rail, and it also wants us to sanity check the 5 volt rail. So let me move the camera and we'll check those real quick. Looks like somebody may have added an R606 to this unit, so that's interesting. Where's ground? 15.17, so we're good there. I'm allowed 14.3 and 15 set in between 14.3 and 15.7. 15.1 is fine. We are good there. Here's our 15 volt test point right there. Now we'll do the 5 volt test point. 5.2, and I'm allowed 494 and 546. So that's healthy there. I'm picking up ground just from the chassis down here. Okay, so power rails are fine. Okay, here's our main tuning capacitor. We're looking for as close to 1 megahertz as possible. This is not a 10 megahertz reference clock. This is a 1 megahertz reference clock, so 1 microsecond. Too much capacitance in that screwdriver. That's throwing the measurement off. All right, it's broken loose. Since we are tuning an oscillator, this is going to be very touchy. Well, we're off by 30 millihertz, 1.03 megahertz in terms of the reference, so I can't ask for better than that. But it looks like I'm allowed a swing of 20 hertz. I'm allowed a swing of 1 megahertz plus 10 to 1 megahertz minus 10. I'm at 1 megahertz 0.028. I'll show you that here right now. Okay, there's our measurement, 10.135. And it's still counting down a little bit. Okay, now that we have the reference set, I need to check all the time markers between 10 nanoseconds and 5 seconds for correct amplitude and timing. So what I'm going to do is we're going to run through it real fast. Going to check the timing on the frequency counter. We'll check the amplitude on the scope. So I'll run it completely up and then we'll run it back. But we'll have a little fun and we'll actually look at these. Going to readjust time and period so it matches the front panel of the TG501. We'll look at it in periods. This is 10 nanoseconds. Looks all right. 20. Yep. The oscillator's running a touch fast. Just a touch. It's not perfect, but it's within specification. 50.1. So 100. 200. 500. 1. Micro. 2 micro. 5 micro. 10 micro. 20 micro. 50 micro. 100 micro. There's something wrong with the gate time here. Bring the gate time up. And let's turn on the low pass filter. And there we go. So I've got some noise in the lab again. If the noise is in the if the noise that we've been fighting in the lab is happening right now, I have a pretty good idea as to what it might be, but I need to dig into it a little further before I definitively say this is the problem. 200 micro. Got a long gate time, so that's good. 500 micro. One millisecond. Yep. 2 milliseconds. Looks good. 5 milliseconds. This is looking really good so far. Yep, that's good. 10. Yeah, that looks good. That is 100 milliseconds. 200 milliseconds. That's good. 500 milliseconds. And that is 1 second. It looks like it's too slow for the counter, so let's move over to the scope. Yeah, the 1 second time marks look good. I might have to single shot this to get this to line up right. Time marks are good. We are on positive slope, which is fine. Back this off to 5. Back this off to 5. Set it up for single shot capture. So there is really not much that goes wrong with these. There it goes. Scope's running. Now it's about to be really slow. So our 5 millisecond time or 5 second time marks are good. So let's speed the scope up. Now I'm checking amplitudes. Everything should be over a volt. We're at 500 millivolts per division. So I am looking for anything over 2 divisions. We're close to 2, so we are doing just fine. Looks good. You can see as I'm backing down the time marks each step. That looks good. That looks good. Nice sharp time marks. This thing is doing very well, especially for its age. Of course, there's not much that, apparently there's not much that goes wrong in the TGs. That's 10 mic, 5 mic, 2 mic, 1 mic, it's starting to come down a little bit. Yeah, we're still above a volt. And that's it. That's 10 nanoseconds. So 10 nanoseconds, we end up right around a volt and a half. So, yeah, 1.4. Not bad. Next is the high-speed trigger amplitude. So we need to move this over to the trigger. .1 mic. Turn measurement on. So we're at 2.16 volts. We need to check the trigger amplitude at 50 microseconds. We're at 2 volts. We're at 2.16. Yeah, I'm not too worried about that. That looks good. Here's what the waveform looks like between the two. Check the variable range now. Doing this slightly out of order. 1 microsecond. Let's get. Okay, so I need to be able to go below 925 kilohertz. We're at 919, so the variable's working. Let's speed it up a little bit. Looks like we're spot on the variable control. That actually looks like it's working very well. Speed this up to the 5 nanoseconds. Now I'm going to move over to the sampling scope. Okay, we have a period. We have a period and frequency of just shy of 200 megahertz. A little bit faster than 5 nanoseconds. That's good. Peak to peak is a volt. Keep forgetting this is a touch screen. Turn off the touch screen. Peak to peak is a volt. So that is looking very good. So I'm not actually going to adjust anything there. Going to move down to the 2 nanoseconds. Now what we're going to need to do is waveform. Actually, we'll just make it reacquire, because I'm going the wrong way. Oh yeah, turn touchscreen back on. Off. Measure. And yeah, we have a frequency of 500 megahertz at just under 2 nanoseconds of period, so that's fine. Now let's check the 1 nanosecond. This is the one that's really hard to measure without a sampling scope. I thought these were having trouble when I was looking at the other scopes, but it's just because I didn't have anything in the lab that was fast enough. Gotta turn the touchscreen on. I wasn't sure how much use I was going to get out of this DSA when I initially got it, but I needed it for the 284s. I'm going to get a lot of use out of this for sure. I have it building some averages, so it cleans up the waveform, especially with the noise in the environment, so hopefully we can average out some of that noise. But I need over 200 millivolts peak to peak on the 1 nanosecond marker, and over 700 millivolts peak to peak on the 2 nanosecond marker. So let's see what we've got. We're at 335 millivolts peak to peak on the 1 nanosecond marker, so that is good. Let's see where we're at on the 2. Back this down a bit. Oh yeah, we're over a volt peak to peak on the 2 nanosecond marker, so perfect. So that actually checks out. Everything is good. Didn't have to adjust any of the capacitors in the high frequency section, so that is awesome. Thanks for stopping by the lab today, taking a look at this TG501 time mark generator. Not much went wrong in this unit, so there's not much to go wrong in this unit. Not a lot to rebuild one of these, so he's ready to go back up to the enclosure to help me calibrate some more scopes. So I will see everyone in the comments below, and I will also see you in the next video.